Hello everyone! In the last article we plotted some nice graphs with gradient fields on the bottom. Today we will see how we did that. Specifically, we will see how to plot vectors and vector fields in 2D, how to plot a surface in 3D, and how to plot a gradient field in the bottom plane when we have a 3D surface. We did the lesson today directly on the notebook, on the Jupyter notebook, where we can see the codes running, being implemented and crashing all over. All we need for educational reasons. So let's kick start by importing the relevant library. We will use some NumPy, we will use matplotlib, the pyplot, the one that we are very used to know. And to do 3D surfaces, we use this another model, it's an object on the matplotlib, the mpl toolkits.mplot3d. We import axis 3D. Axis 3D is a special pyplot object which will be instantiated when called an axis, like with subplot. And we do that by choosing the parameter projection in the subplot as 3D. We'll see it later on. The main character today is a pyplot method called quiver, which is called on axis objects. We can call plt.quiver and it admits 4 main parameters x, y, u, and v, which are very easy to understand. So x, y are the coordinates of the base of your vector and u, v are the coordinates of the tail of the vector. Sorry, u, v are the coordinates of the head of the vector. As we think of a vector as an arrow, so it has a head and a tail. So the first two coordinates are the coordinates of the tail, so from where it starts, and the last coordinates, it is where the arrow ends. So say we have 0, 1, the first two coordinates, and 2, 3, the last two coordinates, and we get an arrow from 0, 1 to 2, 3. The method itself is much more flexible than that, so the x, y, u, v, the 4 parameters, they don't need to be exactly scalars. You can put lists, arrays there, and it will work the same. Say, for example, we have 4 vectors which we want to plot. We do not need to call the method 4 times. We don't need to do an plt.quiver for the first, plt.quiver for the second, etc. We just need to input each of the coordinates, the x, y, u, v, the 4 parameters, as a list, so the coordinates appears in the right order. Let's take these vectors for instance. So the starting point, the base point, the tail point is 1, 0, 2, 0, 3, 0, and 4, 0, so 4 vectors. And the head, the final point, is 5, 3, 6, 3, 7, 3, 8, 3. So take a minute to imagine how to read these vectors, and then we plot them. As mentioned, you don't need to do one per vector, and by the way, it's easy to do one vector. You don't need to retype everything, you can just unpack them, yeah? Just for fun, let's do that, and yeah, that works. But much better than that, we can pack all the x coordinates in one list. So we write x, so the x, this is the base point, the first coordinate, so 1, 2, 3, 4. Then we have y, this is the second coordinate of the base point, so it's just 0, 0, 0, 0. U and v. Once this is done, we can plot directly the quiver. Write in plt.quiver, so x, y, u, v. And here it is. We have a plot with 4 arrows, exactly as we want, more or less pointing the direction we want. If you think though about these arrows, it has nothing to do with these arrows here. if you think on this first arrow, it would start on 1, 0, which is starting, it's good. But the final point is 5, 3, so the x would be something like here. And the 3, God knows, because the scale is so messed up, you see? So that happens because the quiver method, it computes some kind of algorithm to choose the size of the arrows and all that. It is a very straightforward way to correct that, and it is to change 3 parameters. So it has a parameter called angles. So angles can have either xy, or angles can have the value uv. It's these both values. Then it has a parameter scale, which we set to 1, and it has parameter scale units. It has much more other parameters, okay? It's really a very rich method. You can check on the documentation. And once you do that, then things seems much better. Well, this is not very good because our graph is not getting the whole structure, so let's alter a little bit here. Let's not put on just on PLT, we can use some axes, so we can change the limits. Or we can use just PLT.xlim, and let's see, something like this, from -1 to 12. Yeah, it's looking better. And PLT ylim from -1 to 5. That's because the greatest y is 3. Yes, so again, you have it, and this is still not exactly what we want, if you think a bit. And that is because we changed the angles. The angles parameter, it changes a little bit what the UV does. As we said before, an arrow, a vector, is just an arrow. So it's something pointing from a starting point, initial point, to a final point. And when we were typing before there, the first 2 coordinates would be related to the first to the coordinates of the starting point, and the second 2 coordinates to the end point. So the xy and the uv, right? When you use angles equal to xy, the u and v, it changes a bit. So you are not anymore writing the first coordinates. Well, you are. So the xy, it steals the coordinates of the tail. So the starting, the beginning coordinates, the base point. So xy is related to the base point. And uv now, it's like a tangent vector. Now uv is a vector with coordinate, first coordinate u, second coordinate v, is starting at the point xy. So in the end, what you are getting here, it's a sum, all right? So the end point here, it will be the sum of xy and the uv that you typed. So let's see. So the first vector here, it starts on 1, 0, which is here, 1, 0. And now to end not on 5, 3, but the 5, 3 translated to the point 1, 0. Yeah. So we take the vector 5, 3, which would start on the 0, 0, like here, 5, 3. Yeah, 5, 3, like this. And then we translate it to the 1, 0. All right. So 5, 3 is like this. 5, 3. So we get the first coordinate 1, 1 plus 5. So this coordinate should be 6, yeah, which is here. So the first coordinate of the first vector here, the end coordinate is 6. the first coordinate, and the second coordinate of the head of the first vector is 0 plus 3 is just 3. Okay, so it is summing. All right, it's not anymore the vectors we were dealing with, the ones we want. So if you want the original vectors, the ones that start on x, y, and end on u, v, what we do, we just subtract from u and from v x and y. And if you are using NumPy, it's very easy to do, so we just convert everything to arrays and we can just subtract it. So we write some u new is equal to the u, the old one, minus x, because it will sum x, so the v new, it is the old v minus y. And now in the plot, we change the u to u new and v new. And let's plot. Aha, now it's looking better. Yeah, so now it is exactly what we wanted. So 4 parallel arrows, which are exactly the ones that start on this point and end on this point with the right scale and the right everything. This is really the 3 in the data unity, the graph unity. This is really 6 and all that. Okay, now all is good. The next topic we deal here is about plotting vector fields. A vector field is a family of vectors. You have one vector for each point in the plane, or each point in its domain. Maybe it's not defined the whole plane. Yes, so usually what you have an explicit expression, explicit association rule, a function that it inputs a point in the plane and it outputs the vector, which should be seen as a vector coming from that point. And the example of it is the gradient field, like in the plots from the previous article, are vector fields. So of course we have infinite vectors talking like this, and we cannot populate an axis with infinite vectors, but nevertheless we can define the rule for the vectors. It make our life very much easier, and we can plot a grid of them. We will illustrate here how to plot a vector field with two fields which are from classical mechanics. These are the two fields very close to my heart. The first field is of an infinitesimal rotation. So if you rotate the plane like this, or like that actually, you'll get a vector field that indicates the movement of each particle. Yeah, and the second field is the field that you get from the phase space of a pendulum. So you have a pendulum going tick-tock, tick-tock. This is ruled by a second order differential equation. Of course, you don't need to know anything of this to do Python, right? If you just want to plot the graphic, you just hear it as music for your ear. So the phase space, it plots the momentum and the position of your pendulum. So if you put the two of them together, the momentum and the position, so you have something in the plane, and your second order differential equation becomes a first order differential equation, which is a vector field, if you did major mathematics. Right. So we do the full nonlinear pendulum. Maybe if you are a physicist, you see the pendulum and, well, not physicist, but if you did not much in physics, the first equation, actually, the infinitesimal rotation, it is the simplified pendulum phase space. Okay. The second is the full thing. Let's start by defining our functions then. So we define the functions that inputs points in the plane and outputs the vector of the vector field. So the first one, we call it infinitesimal rotation. So it takes a pair of coordinates, x and y, and it will give you a u and a v, which are the coordinates of the vector field, so the head of the arrow. So in the case of infinitesimal rotation, this is like multiplying by I if you have well, if you know this connection with complex geometry or complex linear algebra. So the first coordinate of the vector, it will be actually the second of your point, and the second coordinate of the head of the vector, not really the head, but the vector itself, be minus the first. So we will return a pair uv. It will be very convenient to us, and equivalently analogously, yeah, in analogy, we define the phase pendulum like this, and now again we have u and v, but the u is some y and the v, it is the sign of the first coordinate, so the sign of x. And we will not use math.sign here, we use np.sign, because we'll be very weasel and not put scalars on this x and y, we will put matrices. And again we will return uv. The next thing we want are a grid. So for which x and which y's we should compute these vectors on the vector field. Okay, so let's compute the x from -5 to 5. So we have this interval from -5 to 5, and let's take a number of x's there, okay, of values of x. NumPy again has a very nice solution to how to write this. So the values of x, we take an array given by lin space, and our boundaries from -5 to 5, and let's start by taking 30 markers, 30 values from -5 to 5 for the value of x. And for the y, let's take the same, so lin space from -5 to 5, 30 values. But now we need pairs of coordinates, right? If you think a little bit now, if we put x and y in the inputs of the quiver, if we do like this, x, y, so uv, whatever it is, what will it will give us 30 points. Yeah, it will give us all 30 points in the same coordinate, in the same line. Let us do that, just to show how it doesn't work. Yeah, so if I input x, y here in the infinitesimal rotation, it will compute exactly these things. So the y and the -x for an array, everything makes sense very well. So everything works well, just putting NumPy arrays here. So it inputs a list with two guys, and these are my u and v. So let's put uv here, and we need these 3 parameters from the quiver, which are the angles, just to say that we are speaking about vectors that start on that base point. So our u and v are not final coordinates, but is the vector that you must translate the x, y to put there, and these scale parameters. Yeah, let's see what we get here. And yeah, you see, so you have a line of x, y. Why you have it? Because the first coordinate here, the first guy here, and the first guy here are the same. Yeah, so if you print x and y here, you have two arrays with exactly the same numbers. So they lie in this line x equal to y, right? This is not exactly what we want. if you agree with me, right? We would like to populate this whole thing. So to populate this whole thing, what we do, what we really would like to have is that for every value of x here, you have a pair with every value of y. And again, fortunately, NumPy provides a solution for that. So we have mesh grid x, y. So what mesh grid will do? It will output two matrices to be 2D arrays, and that's not an issue. And these 2D arrays, they will give us the coordinates of x and the coordinates of y, exactly. So sorry, it's not u and v, it's x and y. And now let's change here also, or let's not change, let's do like this. uv is equal to infinitesimal rotation x, y. Now capitalizing everything, x, y, uv, and that's cool. Much better, isn't it? So can you see the rotation? So the vectors are quite big here, all right? And it's hard to see that they are actually equal. They are like in a square, they are equal width and height. The x and y coordinates, they are equal. So let me change here, scale, and if we increase this number, it will decrease the vectors. Yeah, something like that's good. Yeah? What do you think? You see, it's a rotation. Nice, right? Even nicer, I think, is the, not the rotation, but the pendulum. So let's put u pend, v pend is equal phase pendulum of xy. Right. And here, let's put repeated quiver, xy, u pend, v pend. Let's copy and paste these guys here. You see? So the pendulum has a sign on the x direction here, which makes the thing periodic. So this figure, starting from here and ending from here, it repeats infinitely all around the plane. We can even have a better look of it by expanding the limits and expanding the plot itself. Yeah. So let's put here 15, 15. And what else we need? Oh, this is good. So it gets very deformed here, right? And here 15, 15. So yeah, you see, kind of, right? If we do a figure, fig size 55, it should be better. So now it's from -15 to +15. I think there are too few arrows. Yeah. And the arrows, you have to tweak it a little bit, so it will be nicer with it. Yeah, you see the pattern now? It's repeating, yeah? It's very nice. So this is the phase space of the pendulum. So if we start with your pendulum in the initial state here, for example, so it will start moving and the velocity will go up, and the linear position, the x, yeah, it will increase, and keep it moving like this, right? So the x will always increase, but I think you have to interpret that as an angle. Yeah. So this is a very big movement, I think. It has a lot of velocity. So you have your pendulum starting like this, and with a lot of velocity, so it's doing like this. Something like that, it seems so. All right. And this is all about vector fields in 2D. Let's talk about plotting surfaces. So 3D, yeah? So 2D surfaces in the 3D space. Or how to plot a graph of a function in a 3D space. So first things first, we define the function itself. So the input, again, a point in the plane, and we output the value of the function. We will use a function here, which I kind of tweaked it, I fine-tuned it to have two minima. Yeah, so I'll have that surface that you saw in the last article. And so this is in the x, this is a fourth order polynomial with roots in 0, in 2, in -2, and in 1. That's how I came up with this formula. And in the y, it's just a parabola like this. So if you see on the y-axis, in the y direction, it's just like this. And on the x direction, it is a more complicated polynomial. All right, since it's fourth order, it increases very fast, decreases very fast. So I kept to a very small limit of points, so from -2 to 2, to plot the surface that we had there in the last article. And here again, to plot the surface, so we want to plot a surface, a 2D surface in 3D space. So our plot, our axis will not be like this with 2 axes, we'll have 3 axes. And the plotting, I don't know if you ever plotted a function in 2D space. So to plot a function, you choose a lot of points, a lot of values in the x-axis and plot for each value. We will do the same here, but again, we have to choose a lot of x values in the plane. So a lot of points in the plane. So again, we would use a grid, the mesh grid from NumPy. So we take some points, let's take 40, just to not take 30. Some points from -2 to 2. As I told you, I chose this -2 to 2 just for statistical reasons, because the function itself, this fourth order polynomial, it increases too much, too fast. All right. So we will use a mesh grid. Why are we using a mesh grid? Again, because we need a lot of points in 2 coordinates, not only 1 coordinate. So the mesh grid will output again 2 arrays full of coordinates, and when you get one entrance on the X array and the same entrance on the Y array, this will be your first point, your first pair of coordinates, which give you the first point. And the last thing is that we want the third coordinate. So if we are plotting something in 3D, we need 3 coordinates, not only 2 anymore, right? And the third coordinate, what is the third coordinate in the graph? It is the value of the function. So again, fortunately, our function is very robust. The operations we are doing here, they are done entry-wise in a NumPy array, and that's what we are inputting here. So we have the z, and the z will be again an NumPy array, which we can plot. Okay. Now, best thing is to define a figure. So plt dot figure. I'll put some size here, because when I put on the notebook, I always find it quite small. And on the figure, now we will put an X on it. So add subplot, so 111. And now the magic that makes it 3D is this parameter projection is equal to 3D. So remember in the beginning of the video, we just imported this npl toolkits.mplot3d import axis 3D. Okay, you could just import the npl toolkit. It works the same, like that. Okay, so when you add this projection 3D, it's not anymore a usual axis, it becomes a 3D axis. All right, and now the surface, it is plotted on the axis by the method plot surface. So x.plot surface. Now the plot surface, this is our guy, right? So this is what will give us the surface on the 3D space. So what does it need? It needs an x first coordinate, the second coordinate of your points, and the third coordinate. So this x, y, and z, they must have the same shape, all right, in a way that your PyPlot will understand, okay, the 1, 1 entry of x is the first entry, is the first coordinate of the first point, and the second coordinate of the first point is the 1, 1 entry of y, and the 1, 1 entry of z. Yeah, so they pick it from the same position, right? And if we just run it, it didn't crash. Very good. And we have our surface. All right, looks very good. Yeah, isn't it? It's very blue. There is something, well, literally magic. Yeah, so if we put matplotlib notebook, if you are in a Jupyter notebook, then when you run it, you have an interactive plot. It's not anymore a statical image, you can just rotate it. Yeah, you see? Nice, huh? Nice, right? Okay, so a little bit to get to what I had there in the first article. So the color map that I was using is called blues. I find it a little bit more expressive because you can see better what is the minima, where the function is big and where the function is small. Yeah, because the color changes more. All right. I also include this option here, antialized equal to false. It improves a little bit the speed. So it makes the surface look a little bit worse, but improves the speed if you want to move it around. Okay, and very useful when you are plotting other things around the same axis is to put an alpha, so it is a little bit transparent. Yeah, so the smaller the alpha, more transparent it is. So in the article you see how to plot a tangent vector, how to transform a vector in a tangent vector of your surface. So a vector in R2 on the xy plane down here. You can choose any vector here and just translate it and transform it in a tangent vector. So if you have a vector here, it will be a plane vector. when you transport to the surface, it will be a little bit skewed up, yeah, to be tangent. Otherwise, it will not be tangent, to be something escaping from the surface. All right, you'll see all there. You see how to put a color bar here on the right side, okay? It's all there on the article. Here I will concentrate on the task of putting the gradient on the bottom. So again, the gradient field is just a vector field as any other vector field. And the best way to do that, to plot it, is first defining it. Yeah, so we have a function f. We just define the gradient of f as something that takes 2 points, inputs a coordinate, a pair of coordinates in the xy plane, and outputs the gradient vector that's supposed to be in that pair of coordinates. In the particular case of the function we have, the gradient is quite big, so I will not write it down by hand. I just copy and paste here. So this is the gradient, okay? How you compute the gradient? It's just in Euclidean coordinates. You take the first the dx derivative and then dy derivative. The first coordinate is the dx derivative, second is the dy. Now we actually already have the x and y coordinates. We have the base point coordinates for our vectors, for our quiver. What we don't have is the vector coordinate. Yeah, but the vector coordinate is now on the grad of x. So we can write uv. Now this is grad of f of x and y. And again, if you see here, an NumPy array will just work out very well entry-wise, and that's what we want, yeah, that it gets multiplied entry-wise and gets subtracted entry-wise and all that. So the grad of f directly applied to our xy, which are already here, will work perfectly. Now, if you think a little bit, we are not more in the 2D, we are not more in the plane, we are in 3D space. So our quivers, our vectors, they have 3 coordinates, right? We have an x coordinate, y coordinate, and a z coordinate. And so both the base point and the gradient, the vector point, they have 3 coordinates. Right? Our coordinates here, let's call it z0. Okay, z0, and I will just put any coordinate that will represent this bottom part here. Yeah, so here there is a -6, so it's a little bit after -6. So if you see the scale here, this part, it means 2. Yeah, it's 2 units. So this looks like half of this. So let's put -7 as the z coordinate for our vectors. All right. So let's write here np dot zeros like x. Yeah, so we have something exactly like x, and now we subtract 7. So it will be a matrix, a 2D array full of -7s, and this will be our z coordinate. All right. Now the 3D plot, it doesn't have anymore the angles parameter. Okay, so what we do, we will plot the 3D, so x, y, z0. These are the coordinates, the base point coordinates of our quiver. So this is a big set of coordinates. I think there are like 40 times 40, 1200 coordinates there. And so these 1200 vectors, they will be distributed on the xy plane, yeah, with coordinates x, y, and z0. Remember, the z0 is just -7. Yeah. And now for each coordinate, I want a vector that goes from there, and it is exactly the UVZ0. Okay, the vector going out is UVZ0, right? So whatever we write here, so if we write UVZ0, what we will get here is that the end point of the vector will be UVZ0. Okay, so this parameter here is the head of the vector. Okay, the head of the arrow. It is not the translated thing as we wanted. So what we will do here, we will subtract things. So, sorry, not subtract, we will translate it. We will translate the u, v, z0 vectors manually. So x plus u, y plus v. So the vector itself was supposed to be x, y, 0, the gradient vector. So it was supposed to be a 0 here. All right. So the 0 makes no difference. We put z0 plus 0. Okay. And I will put one parameter here, otherwise to be very messy. So this one is sufficient. And we get it. Yeah. That is a lot of factors. Again, very messy. Let's tweak a bit. Line width equal 0.6. We can make it a little bit smaller also. Yeah, that's it. Now it's looking much better. Maybe we can make it bigger. That's too big. 15. And we can put some nice color just to change here. So dark orange. Yeah, here. Voila, our gradient. Okay, so the gradient is well depicted here. Okay, so you start here. If you start here, you move on this direction in your gradient descent. Okay, sorry. If you move this direction on your gradient, if you follow the gradient. If you want a gradient descent, then your vector that you are translating for that point is not the gradient, so it's not uv, this minus u, minus u, minus v. Yeah, so this is the direction for gradient descent. You see? So if you start here, it will throw you towards this minima. Yeah, is it clear? Otherwise, if you start here, look at that, if you start here, it will throw you to this minima. This other minima, more or less here. Okay, so the domain point of this minima is more or less here. All right, otherwise, if you start here, just in the middle of the tool, it will throw you here, which is not a good point. It's a saddle point. Yeah, so this is not a minima, not a local minima, it's not a maximum, it's just a saddle point. You see, the gradient is 0 here, and the gradient does throw you here if you are very unlucky. So it's just on this line. If you get perturbed just a little bit, you just go to the others. But otherwise, you can just get stuck in the saddle point here. Alright, so saddle points are unlikely to happen in machine learning gradient descent, but undesired minima, they can happen. They indeed can happen. They are very stable, so around themselves, they are attractors. Okay, they will get your algorithm converging to them. You'll never be able to escape to pass this saddle here and go to the other. Okay, which is the global minima here. All right. So I hope it looks good for you. I hope it helped you a little bit. And keep logged here in our blog. We like very much everything we have. See you next time.